So we're talking about the composition of worlds, talking about the world itself, but the atmosphere of the planet is also interesting to study because, after all, that's the part that we interact with on Earth. You breathe air all the time, and so that turns out to be a very important sort of thing. The terrestrial planets, Earth's atmosphere is mostly oxygen, nitrogen. We have small amounts of argon, methane, carbon dioxide, and so forth. It's mostly oxygen, nitrogen, and argon actually the next most common thing, just an inert gas. Venus and Mars have atmospheres that are very rich in carbon dioxide. Now, the interesting thing is Earth has a lot of CO2 as well, but most of the CO2 on Earth has been bound up and it's been pulled out of the atmosphere. It's been done by either geologic processes or by biological processes. But if you were to release all that stuff back into the atmosphere, Earth would have an atmosphere that is very much like Venus and Mars, mostly CO2. Most of the oxygen in Earth's atmosphere actually comes from the degradation of the CO2. It's O2. Take the C away. Okay. And so the Mars has some nitrogen in the atmosphere. Venus has an atmosphere that's about 90 times thicker than Earth's atmosphere, but it has the same amount of nitrogen in the atmosphere as Earth does. It just has a huge amount of CO2 in the atmosphere. Titan, which is not really a planet, but it is very similar in makeup to a terrestrial world. Titan has an atmosphere that is mostly methane, nitrogen and methane. Sorry, it's mostly nitrogen, but like Earth's atmosphere, but it's got a lot of methane in it as well. Okay, the gas giants are primarily hydrogen, helium in the atmosphere, and they do have tiny amounts of carbon and methane. The carbon will mix, if you mix with oxygen, you get CO2. But if you mix carbon with hydrogen, you can get methane. If you mix nitrogen with hydrogen, you get ammonia. And so that gives you some of the clouds that are in those worlds. Now, why is this the case? Why? Well, this has to do with physics. In physics, we realize that there's a certain escape velocity. The escape velocity is how fast you have to be going to get away from something. And so that's equal to the square root of 2 times g, which is a gravitation constant, times the mass of the world divided by the radius of it. The bigger the mass, the harder it is to get away. The smaller the radius, the harder it is to get away. The moon has vastly less, it has a little bit less radius, about 1/4 the radius, but it's got 64 times less mass than Earth, so it's much easier to get away from the moon than it is to get away from the Earth. That's why the Apollo rocket that went to the moon, the Saturn V, was a huge rocket that left Earth, but a very small thing left the moon. In physics, we also learn about kinetic energy. Kinetic energy is 1/2 times mass times velocity squared. So the more mass you have, the more energy, the more velocity you have, the more energy. I often refer this to like gas mileage in vehicles, that ignoring air resistance, which is a major factor, that and also ignoring engine efficiency, another major factor. Simply, if you have more mass, it takes more energy. If you go faster, it takes more energy. So if you drive slower, you actually have better gas mileage than if you drive fast. And also, if you have a lighter vehicle, you have better gas mileage because it takes less energy to make it go. Now, that's one strategy a lot of automakers are doing. I don't like that idea, but that is to save mass to increase gas mileage. They leave the spare tire out of the car. I don't like that idea. Thermal energy. In physics, we learn about thermal energy, and that is the energy is 3/2 K. That K there is called the Boltzmann constant. It's just a constant of nature times T. The T is the temperature in Kelvin. So the higher the temperature, the higher the energy. Well, then what we realize is the higher the temperature, the higher the energy. The higher the energy, then that means 1/2 mv squared. So if m is less, v has to be bigger, okay, in order to get that energy. So that means that light molecules actually move faster than heavy molecules. And then if they move fast enough, they achieve escape velocity. So imagine this. Hydrogen has weight 1. You know, hydrogen H2, that's weight 2. Okay, that's how you normally find hydrogen in a gas. Helium has weight 4. Nitrogen is 14, but N2, which is normally how you find it, is 28. Okay, oxygen is 16, but you normally find it as 32. And carbon dioxide, that's O2, that's like 32, plus carbon, which is 12, so that's weight 44. Okay, so these are molecular weights. Now notice there's this huge gap between those two at the top and these down here. Okay, that is why Earth, even though hydrogen, helium, those common things in the universe, Earth doesn't have much of it, because those things are so light that they achieve escape velocity and leave Earth. That's why helium is so rare on Earth, is that when it gets loose, and it's really weird, we play with the stuff, but we don't make new helium. It's a finite amount, and so if it gets out of a balloon or something, it floats to the top of the atmosphere. It's lighter than nitrogen and oxygen. Achieves escape velocity and leaves Earth forever and ever and ever. The only way you make more helium is like detonate a hydrogen bomb or something. A little bit of radioactive decay will make helium too. But again, you know, these are typically not environmentally friendly ways of making helium. Nitrogen and oxygen are much heavier right there. And so nitrogen and oxygen will tend to hang around, you know, a little bit better. Okay, but even the moon, Mars has less gravity than Earth, and so Mars has trouble hanging on to even these things, particularly because ultraviolet light from the sun splits them apart into these lighter things, and they leave. Okay, and so Mars is able to hang on to the much heavier CO2. Okay, and so that's how it does. Now, here's the interesting question: Titan and the moon are about the same size. But our moon has no atmosphere at all, because our moon is so light it cannot even hang on to CO2. So pretty much all gases eventually escape the moon. Now, they'll hang around for a little bit until they achieve escape velocity and leave, so I mean, it would hold onto an atmosphere temporarily, but it wouldn't keep it. Okay, but Titan has an atmosphere of nitrogen, okay, and methane. How does it do that? Well, the way it does that is it's a very long way from the sun. It is 10 times almost farther from the sun than Earth is, which means you get 1% of the sunlight, 1% of the solar heating. That means that it is so cold there that the molecules are not moving very fast, and so they're not achieving escape velocity. So that's why it's able to hold on to an atmosphere. So there we have atmospheric compositions, and the reason the plants have the atmospheres they have has to do with the physics of how these things work. Now, the big question on Earth, though, is why is our atmosphere got so much oxygen in it? Because oxygen is a very dynamic molecule. It tends to bond up with other stuff. We have oxygen because something keeps pulling it away from the carbon. Okay, the oxygen of the atmosphere wants to bond up with stuff and make carbon dioxide, but something is pulling it away. That something is largely biologic activity. And so plants, in other words. Though biologists dispute when I call them plants because they're like cyanobacteria. But anyway, plant-like stuff, photosynthesis. So that's why our atmosphere is kind of the way it is. But we'll get to that later.